In this video, we will review L'Hopital's rule. So to start with, let's look back at the statement. If f of x and g of x are both differentiable functions, and we have either of the following conditions. First, that both the limit as x approaches a of f of x and the limit as x approaches a of g of x are 0, or if both of these limits are equal to either plus or minus infinity, then we can apply L'Hopital's rule, which tells us that the limit as x approaches a of f of x divided by g of x is equal to the limit as x approaches a of f prime of x divided by g prime of x. With this in mind, we talk about 0 over 0 or infinity over infinity. We call these indeterminate forms. So when we think about an indeterminate form, that's when we then want to move on to using L'Hopital's rule. So some examples where we can see this right away is if I look at the limit as x approaches 1 of ln of x divided by x minus 1. Notice that ln of x is going to approach 0 as x goes to 1, and x minus 1 is also going to approach 0. So this is of the indeterminate form 0 over 0. I can use L'Hopital's rule. And it's good practice to indicate when you are using L'Hopital's rule. I'll put an LH here over the equal sign. And what I want to do here is take the derivative of the numerator, ln of x. That has derivative 1 over x. And we're dividing that by the derivative of x minus 1, which is 1. And here we no longer have an indeterminate form. Instead, I can simply plug in x equals 1 to see that this limit will approach 1. Another instance where we could use this is when we look at the limit as x approaches infinity of x squared over e to the x. Note that this is an indeterminate form of infinity over infinity. Both the top and the bottom function approach infinity as we send x to infinity. Again, I can use L'Hopital's rule. The derivative of x squared is 2x, and the derivative of e to the x is e to the x. What happens here is that I again have an indeterminate form, still of the form infinity over infinity. What this means, though, is that I can simply use L'Hopital's rule again, and essentially we can use it again and again until we no longer have an indeterminate form. In this instance, that happens in this very next step. Here, the denominator does still approach infinity, but the numerator doesn't. It's constant, it's 2. So as the denominator grows without bound, 2 divided by that is going to approach 0, which ends up being our limit here. So these are some kind of classic examples of L'Hopital's rule where we're presented with the limit that's already in the form that we might look for, 0 over 0, plus or minus infinity over plus or minus infinity. And the reason we think of these as indeterminate is that we have an idea of what we think should happen if we take 0 and divide it by something. We think 0 divided by something should be 0. But we also have the idea that something divided by 0 should either be undefined, or if we're talking about limit notation, that should potentially be infinity. And so the numerator and the denominator both approaching 0 contradict one another. And there's a similar idea with infinity. The numerator is growing, so we would expect the total fraction to grow. But if the denominator is growing, we expect the total fraction to shrink. So carrying that idea forward, there are other types of indeterminate forms where you have kind of contradicting behavior. We call these other indeterminate forms, but they're a little bit more complicated because we have to restructure them in order to use L'Hopital's rule. In order to use L'Hopital's rule, I have to have a ratio of two functions, either of the indeterminate form 0 over 0 or plus or minus infinity over plus or minus infinity. So one type is if you have a product of two functions such that the limit of one of them is approaching plus or minus infinity and the other one is approaching 0. Why is this indeterminate? Well, something times infinity we expect to be infinity, and something times 0 we expect to be 0. So what happens here? Well, it is indeterminate. I cannot simply start taking the derivative of things because it is not in the form f of x over g of x. So the strategy in a case like this is to rewrite it so that it is a ratio. So here I have the limit as x approaches 0 from the right of x ln of x. The from the right is important because of the ln of x function not being defined for negative values of x. Now, as I send x to 0, notice that, of course, x will go to 0, and ln of x is going to approach minus infinity. So this is an example of this form. So the strategy when I have this is to try to rewrite the expression so that it is in the form where I can apply L'Hopital's rule. So if I want to take a product and write it as a quotient, I can do that in this instance by saying that multiplying by x is the same as dividing by 1 over x. Now, notice that the numerator, ln of x, is approaching minus infinity, and the denominator is now 1 over x, and it's approaching infinity as I send x to 0 from the right. So we have an indeterminate form now of the type we talked about above, and now I can apply L'Hopital's rule. The derivative of ln of x is 1 over x. The derivative of 1 over x is negative 1 over x squared. Now, you want to be careful and not continue to take derivatives here because we can simplify this. If I now multiply by the reciprocal of that denominator, what I really have is the limit here of negative x. And I see that as x approaches 0 from the right, this is just going to approach 0. Another type of indeterminate form is infinity minus infinity. So for finite numbers, if you subtract something from itself, we get 0. But that doesn't necessarily hold when you have infinity minus infinity. Again, the contradiction here is that normally we think infinity minus something should always be infinity. And on the other hand, something minus infinity should be negative infinity. So these two things are contradicting each other. So how do we approach something like this example? Notice that secant and tangent, which both can be expressed as something divided by cosine, those are going to have this infinite problem at pi over 2 because of the fact that cosine of pi over 2 is 0. So this is an infinity minus infinity type example. And it's hard to know how to quantify this. The strategy in this situation is to try to condense this into a single expression. Again, like the example above, I'm hoping to get a situation where I have a quotient. And what helps is to recall the way that we define these. So secant of x is 1 over cosine, and tangent is sine over cosine. So notice that I can rewrite this limit by combining those expressions. They have the common denominator of cosine. So in the numerator, I would get 1 minus sine of x, and in the denominator, I would get cosine of x. Now, think about what happens to the numerator. Sine of pi over 2 is 1, so 1 minus 1 is 0, and of course, cosine of pi over 2 is 0. We are now back in the situation of an indeterminate form to which we can apply L'Hopital's rule. Doing so, we're going to get that the derivative of 1 minus sine of x is going to be minus cosine of x. And the derivative of cosine of x is minus sine of x. And here, the numerator goes to 0 still, cosine of pi over 2, but the denominator goes to negative 1 now, because sine of pi over 2 is 1. So in this instance, 0 divided by 1, we're going to get 0. So it's no longer indeterminate because both the top and the bottom are not 0. And then finally, the last type of indeterminate form that I want to discuss is one involving exponents. So something that you could think of as 0 to the 0th power, infinity to the 0th power, 1 to the infinite power. Importantly, these are just a representation of the form. It's not truly the number raised to that exponent. We're saying what the base is tending toward at the same time as the exponent is tending toward something else. Again, the contradiction here. Normally, I would think 0 raised to anything is 0. But if you raise something to the 0th power, we expect that to be 1. And you can do a similar analysis with the other two cases here. So that's why they're indeterminate. And we have a special kind of extra step that we want to take when we have these indeterminate forms that involve exponents. And the step we take, we're going to see in hindsight, is useful because it brings that exponent down. So when I'm looking at this problem here, this is of the form 1 to infinity. As x approaches infinity, the part inside of the parentheses approaches 1, and of course the exponent approaches infinity. So as soon as I see this type of indeterminate form, what I want to do is rewrite the expression as e to the natural log of itself. So we can do that because e to the x and ln of x are inverse functions of one another. So when I have this, the nice thing about that is the fact that we can bring this out front because of our log properties. So this is saying we need to find the limit as x approaches infinity of e raised to the x times ln of 1 plus 2 over x. So if we can figure out, so notice the structure here, if I can figure out what this boxed function approaches, what number that approaches, then my final answer should be then the, not the limit, my final answer should be e to that number. So we've changed this now so that my strategy is to focus on that exponent, find the value that that approaches, and essentially go back and drop that in here. Oh my gosh, I keep writing limit. So what we end up having is that my final answer will be e in this instance raised to, just put it here as a placeholder, that numerical value. So what we need to do at this point off to the side is figure out what happens to the part in pink. So this is not equivalent to the line above. This is separate work. We want to know what the limit as x approaches infinity is of x times natural log of 1 plus 2 over x. Let's pause and think about these functions separately. We know x is going to infinity, but the ln of 1 plus 2 over x is going to the natural log of 1, which is 0. But this is exactly the type of indeterminate form that we started with up here, a product of infinity and 0. What was our strategy there? Rewrite it as a ratio. So I'm going to rewrite this as the limit as x approaches infinity of the natural log of 1 plus 2 over x. And instead of multiplying by x, I'm going to divide by 1 over x. This is now of the form 0 over 0. Now I can apply L'Hopital's rule. And let me start with the easier one. The derivative of the denominator is negative 1 over x squared. To differentiate the numerator, I have to use the chain rule, which is going to give me 1 over the inside function there. That's the derivative of natural log. But then from the chain rule, I need to multiply by the derivative of what's inside of the parentheses. That is just negative 2 over x squared. Now this looks very complicated. However, we can cancel the minus 1 over x squared with one of those in the top, leaving just a 2. So this really becomes the limit of what is left, which would be 2 over 1 plus 2 over x. And as I send x to infinity, this will just approach 2. Importantly, 2 is not our final answer. Let's think about what we were doing. 2 is what we boxed in pink. That's what that's approaching. So my final answer here ends up being e squared. And so this is just a recap of the use of L'Hopital's rule and the fact that sometimes it can be used on things that are a little more subtle that we first have to reconfigure in some way so that we can then apply L'Hopital's rule to tell us what that limit is going to be.